Hello friends, I am T2 sir. We are here to answer the question, what is time value of money? Before I begin, I can tell you one thing for sure. Time value of money is one of the most important concepts to evaluate investments. Let's begin this session by asking a basic question. What is better if I get $P today or $P after a year? Of course, I want $P today, but will be happy to take after 1 year if I get compensated by getting return on my initial investment. This R return is an annual interest rate required on per dollar of investment. This interest rate measures time value of money. Now we know that return or interest rate is what measures time value of money. Now let's try to understand the concept of compounding by expanding time period to 2 years. So now the question is how much I will generate if I get my money after 2 years. In the first year, I have grown my investment by 1 plus R times as my investment generates return of R on my investment in the first year. Now let's see what happens in the second year. I generate additional return on my investment and return on my return PR generated in the first year. You may ask a question at this point why this is the case for second year. For that, I would say from the second year perspective, P into 1 plus R is my original investment and it is generating return R on that, which means my original investment has grown by further 1 plus R times during second year. This concept is called compounding, which grows investment by 1 plus R times per compounding period by generating return on original investment and return on return. Did you notice that I just used a new word, compounding period? And you may ask, now what is this? For now, I would say compounding period is the interval at which investment generates return on return. We will discuss this in detail during later periods. Now let me extend the concept of compounding for extended period. How much $100,000 investment would grow in the next 25 years with a return of R per annum? 100,000 investment would grow by 1 plus R times in the first year, additional 1 plus R times in the second year, and another 1 plus R times in the third year. This investment would keep growing 1 plus R times per year for the next 25 years, such that future value is equal to present value multiplied by 1 plus R raised to the power number of years n. Now let me reverse my question. How much you should invest to grow your investment to $1 million in 25 years? In this case, you should simply discount future value by 1 plus R raised to the power n. This is same formula. Only difference is that we are calculating present value rather than the future value. Note, in case of both present value and future value calculation, R is return per annum and frequency of compounding is occurring annually. Now let us change the compounding period to semi-annually, quarterly, daily, or let's say continuously. In this scenario, also I would generate return on my return at each compounding period. Let's say compounding is occurring m times per year. So if R is return per annum, then R divided by m should be return per compounding period. And if investment is for n years, then effective investment period is n multiplied by n. So in this case, our present value would grow by rate per compounding period, means R by m, plus 1 for an effective investment period of n multiplied by m. After understanding this concept of compounding frequency, we will now define a new term, effective annual rate, which is a rate at which investment grows for n period and compound annually to generate same future value. Therefore, 1 plus effective annual rate is equals to 1 plus R divided by M raised to the power M. Now I have one surprise question. What happens if investment is compounding continuously? Means every second your money is compounding. In this case, future value is equal to present value multiplied by exponential raised to power interest rate multiplied by number of years n. Till now, we have discussed that how to calculate present value, future values, using the concept of time value of money, compounding and compounding frequency. You would have also noticed that we have used R or interest rate as a measurement of time value of money. Now let's understand R. The question I would ask myself is that when I am lending or investing my cash for a period, instead of consuming it for my need or leisure today, what I am giving up? The answer is I am giving up my opportunity to spend my cash today and my sense of security because my cash is with someone else. And when I give up my sense of security, I own risk. Therefore, R is a compensation for the investor against the following: real risk-free rate and inflation. This is generally represented by US Treasury yields. Default risk, which means higher the probability of counterparty to default, higher the risk premium. Liquidity risk, which is lower the liquidity, higher the liquidity premium. Maturity risk, which is higher the maturity of investment, higher the risk and higher the premium. R is also referred as required rate of return, which is equilibrium rate required for a particular level of risk. It is also referred as discount rate when future value is discounted, or you can also call it opportunity cost, which is opportunity lost when dollar is used otherwise. Till now, we understood our building blocks of the concept. We learned how to calculate present value and future value. We learned impact of compounding and its frequency. We also understood relevance of R as a compensation against risk. Now we will use these basic building blocks to solve real life problems. In real life, we will have multiple cash flows over the period, such as CF0 as of today, CF1 after 1 year, CF2 after 2 years, and so on. Some of these cash flows might be negative too. Now to calculate net present value of these cash flows, we will discount each cash flow to its present value first, such as CF1 by 1 year, CF2 by 2 years, CF3 by 3 years, and so on. Sum of these discounted cash flow is called net present value. We are using present value concept to solve real life problems. Now let's use the same cash flow to calculate future value. To calculate future value of these cash flows, we will compound each cash flow to its future value, such as CF0 by n year, CF1 by n-1 years, CF2 by n-2 years, and so on. Sum of these compounded values of these cash flow is called future values. Again, we are using the same concept. Now we have used basic building blocks to solve real life problems. As a next step, let's discuss few scenarios to understand further. Scenario 1. What if net present value is equal to 0. In such case, you could calculate return on your investment defined by cash flow. This return is called internal rate of return, IRR. Now let's move to the next scenario. What if all expected cash flows are equal? In such case, cash flows are called annuities. You would have used this concept of annuity to calculate EMIs on your loans. There are two types of annuities. Ordinary annuity is when each cash flow occurs at each end of each compounding period. Annuity due is when each cash flow occurs at starting of each compounding period. Now, this is your last scenario. What if all expected cash flows are equal and time period is infinity? This is basically a scenario of an investment where your investment generates fixed return for lifelong. In this case, present value is equal to cash flows divided by discount rate. With this, we have covered all our concepts. I would suggest, before we close this session, let's recap our key takeaways from the session. First, time value of money is measured by interest rate R on per dollar of investment value. R is a compensation against nominal real rate, default risk, liquidity risk, and maturity risk. Investment means PV grows by 1 plus R times per year to a future value. In the same way, future value is discounted by 1 plus R times per year to a present value. In real life scenario with multiple cash flows, each cash flow is either discounted or compounded by a factor of 1 plus R to calculate PV or future value. With this, we close our session.